Hey CW Apes, Mr. Kennedy here again. Has it been a whole 2 minutes and 2 seconds? It has. This is part 2 of your chapter 16 notes on non-renewable resources. So in this half, we're going to look at coal, we're going to look at nuclear power, right? Try to wrap this up for you as quick as I can. So when you think about coal, it's another non-renewable resource. There's brown coal, which is low heat, high moisture coal that we call lignite. And then there's soft coal, which is high sulfur content called bituminous. And then there's hard coal, which is high heat content called anthracite. So all coal is not created equal. I wonder what kind of coal Santa put in my stocking this year. Yeah, I gotta work on that. Anyways, so coal, well, if you didn't know, it's extracted from mines in the ground. When you think about coal use, the United States currently, uses 25% of the world total of coal. When you go cross country, you can see other countries are even more greedy when it comes to coal usage than we are. And then there's some that use coal very sparingly. Coal ultimately is fossilized plant material preserved by burial in sediments and compacted and condensed by geological forces into carbon-rich fuel. Most of it was laid down in what we call the Carboniferous period, about 286 million to 360 million years ago. I remember it like it was yesterday. It was quite tropical. Because coal took so long to form, it's considered a non-renewable resource because you can't get more of it in your lifetime. I mean, only Mr. Kennedy, who's 4.8 billion years old, has any chance of seeing more coal formed, right? The resources of coal, well, they're vast. There's lots of coal. It's actually pretty easy to find and to get out of the ground. The problem is the mess it makes. All right? A, to get it out of the ground, and B, when you burn it. World coal deposits are 10 times greater than conventional oil and gas resources combined. Right? So I don't know, maybe we should be throwing like lumps of coal into like the gas tank of our car, right? Reminds me of my first car. Like I had to build a fire in there, wait till the water to boil, and then the steam came out, and then it made this weird chuffing sound. I don't know. So the proven resources of coal have been mapped and measured and shown to be economically recoverable. If it's called a proven resource, like you can get to it, that could increase to thousands of years supply of coal if estimates of unknown resources and reserves are actually included with the proven reserves. As far as the location is concerned, check this out. North America has 30% of the world's coal deposits, Asia 31, Europe and Eurasia 33. So we're doing pretty good when it comes to coal. Not so good when it comes to oil and natural gas. But coal, we're good. Okay? Coal mining, unfortunately, it's dirty and dangerous. Between 1870 and 1950, more than 30,000 American coal miners died from accidents and injuries in Pennsylvania alone. So, while it's easy to find coal, getting it out of the ground and doing something with it, that's not so easy and not safe all the time. Thousands have died from respiratory diseases like black lung disease. China has the most dangerous mines in the world, with 91,000 people killed in mining accidents just in 2008 alone. Coal mining itself is destructive. Most of the time when it comes to getting coal out of the ground, it's not a real pretty process. Strip mining is the cheapest, fastest, easiest way to get at coal. So they basically just get a big old bulldozer and scrape the dirt off the top they don't want until they get down to coal, and then they go to work, right? It often makes land unfit, completely useless for any other use. That means no more native plants, no more native animals. You've got a barren moonscape left behind. Acid drainage can damage streams miles downriver. Mountaintop removal, which is what's practiced throughout Appalachia, can cause streams, farms, and even whole towns to be buried under hundreds of metric tons of toxic rubble. This is what mountaintop removal looks like. You could see that there used to be this lush green forest there, and no, like we're just going to come in with our bulldozers and our dump trucks, and we want that black stuff that you see those dump trucks parked on there. That's the coal. So we just move the top of the mountain off, we dig it out, and like there you go. And we go crazy with our dynamite and our bulldozers and our dump trucks, and yeah, that's how we get it. That's mountaintop removal strip mining. Here's another picture of mountaintop removal for coal. So again, you can kind of see the green area that used to be forest, and then the not so green area where the mountain used to be. Okay. Now, aside from the mess it makes when you got to get it out of the ground, burning coal also releases lots of pollution. Coal burning releases radioactive and toxic metals in the atmosphere. Coal combustion is responsible for 25% of all atmospheric mercury pollution in the U.S. Ash from coal combustion is stored in open storage ponds, which are at risk for catastrophic failures and causing millions of dollars of damage and pollution to local water supplies. Coal burning can release sulfur and nitrogen oxides, particulates, carbon dioxide, which contribute to acid rain, air pollution, and good old global warming, right? Clean coal. I know this is kind of like a buzzword. Like what is clean coal? Clean coal technology. Well, carbon dioxide could be sequestered by pumping it into deep geologic formations, which could also enhance oil recovery. And new technologies such as integrated gasification combined cycle captures CO2 as well as removing sulfur and mercury, which would cut down on emissions. So at the end of the day, when we talk about clean coal technology, like we're not talking about a rock that like burns clean. We're talking about taking like the waste from burning that rock and getting rid of it. That's clean coal technology. Flex fuel boilers. This is a boiler, well, where coal can be mixed with biomass fuels to produce energy with less carbon dioxide emissions. Okay. Here's some other examples of coal mines. So this is valley fill from a mining operation over back east. And basically what you're seeing here is they dug a big deep hole to get to the coal, and then they put all that dirt to the side and literally filled in a valley as a result, and then left the hole behind that filled with water. That water is not a reservoir that can be used for fishing or whatever. It's probably too toxic for life. Sometimes here's the Tennessee Valley Authority, coal sludge pond spill back from 2008. So, coal sludge, they pile it up in these big exposed ponds, and sometimes the levees that are holding that stuff back break, and here's a town that was completely wiped out as a result. Okay. Here's another case in point. Sometimes, priorities get a little blurred. And here we have an elementary school that is literally right next to a coal mine, right? Something to think about. Okay. This is an example of a coal sludge containment pond that is literally sitting right above that elementary school I just showed you. Okay. So here is the pond. Here's a little levee that's holding that back. And if this levee were to fail, guess where all that coal sludge is going? You bet. All right. So coal ultimately, it's easy to find. The world's reserves are huge, and they could keep us running much longer than we could run on oil or natural gas. But hey, let's be honest. Coal is the dirtiest fuel source there is. Because of the air pollutants, the sulfur, the carbon dioxide, it's filthy. Okay, so if you're gonna burn coal, you got to do something to clean the exhaust, so to speak. Fossilized bed combustion is one way, that we're kind of looking at the emissions that to control them from coal. So to cut sulfur, nitrogen oxides, and emissions, we're adding limestone and calcium carbonate to the bottoms of these combustion chambers to try to catch some stuff. There's also wet scrubbers and electrostatic scrubbers that are used to clean the exhaust. And then once the exhaust is out in the air, then we got to do something to capture the CO2 that's floating around, those processes we talked about a while ago. So, at the end of the day, coal is filthy. And if we're not careful, if we just burn it with impunity and we don't think about it, it's going to have a serious environmental impact. There could be and should be some alternatives to coal, oil, and natural gas production. Using trash, municipal solid waste as an energy source, well, that can be a viable alternative fuel for coal. Biomass, we've talked about that in previous videos, is a sustainable energy source. That could be something that, could actually be positive and do good things for the environment and replace our dependency on some of these fossil fuels. We can use synthetic fuels such as liquid gas and fertilizers that can also be made from natural gas and other new technologies. Problem with new technologies, anytime we talk about switching over to something, it's usually there's growing pains that come with it. They're expensive, and there's time delays between the introduction of the technology to the point where it's really working smoothly, right? Last area of energy that I want to throw your way is nuclear energy. So nuclear energy, for a while it was considered it was going to be the savior of the world, right? We don't need to worry about our fossil fuel consumption for electricity and all that because we got nuclear power now, and this is going to fix everything. Nuclear power has kind of gotten a black eye of late, and in states like California and across the United States, nuclear power is slowly being phased out. There are a lot of things that have kind of contributed to this black eye, but basically people are afraid the power plant's going to blow up, and you're going to have some sort of Hiroshima, explosion and massive loss of life, or if nothing else, there's going to be a radiation leak, and it's going to spread from here to there, and people are going to get cancer, and there's going to be some sort of meltdown disaster like what we saw in Chernobyl. So people are just afraid of these nuclear power plants. So California alone has passed laws that basically say all nuclear power's got to be shut off and phased out within the decade, and we got to replace that production with something wind and solar power and the like. So nuclear power, how does it work? Well, in order to have nuclear power, you got to have uranium, right? That's one of the problems with nuclear power. Uranium, well, it's a difficult fuel source to find, and the power plants themselves are pretty expensive to build. Now, provided you can find enough uranium and you can afford the power plant, I mean, realistically, nuclear energy has really, really low emissions. You might see this stuff coming off of these towers in these pictures, but that's not like smoke. It's like water vapor. Probably the worst thing that a nuclear power plant kicks out on a daily basis is hot water, right? And again, that's something that a lot of people are concerned about. Nuclear power plants need to be near a body of water. They take in massive amounts of water, use that to keep the reactors cool and under control, and then the warm water comes on out through a heat exchange process, and that can literally change the climate of the body of water that the power plant is near. But that's it. That's the waste that it produces. Anyways, so in 1953, President Eisenhower gave his famous Atoms for Peace speech, and nuclear-powered electric generators were thought to be, like I said, slicker than sliced bread, and here we go. Nuclear-powered generators would provide energy that was basically going to be too cheap to meter, almost free, right? Between 1970 and 1974, American utilities ordered 140 new reactors for power plants, but construction costs were high and there were safety fears. So at the end of the day, very few of those were actually built, and no new ones have been ordered in more than 20 years. The nearest one to us is Diablo Canyon Nuclear Power Plant, and it's due to be taken offline, like I said, within the decade. All right. After 1975, only 13 orders were placed for new nuclear reactors, and all of those were subsequently canceled. In all, 100 of 140 reactors on order in 1975 were canceled, right? Electricity from nuclear power plants was about half the price of coal, but in 1970, but twice as much in 1990, right? Because you had to build the power plant and you had to find your uranium, all that kind of stuff. So if you look at plants on order to plants in operation, like it really never took off like people thought it would. So how does a nuclear reactor work? I'm going to sum it up like this. Like the nuclear reaction generates a whole lot of heat. That heat is, well, it's going to boil water to make steam, and the steam is going to be used to rotate a turbine. That turbine's connected to a generator, and the generator makes electricity. Wow. So most commonly used fuel in a nuclear reactor is uranium-235, a naturally occurring radioactive isotope. It occurs naturally in 0.7% of uranium ore, but must be enriched to 3% in order to be used in the reactor. We form this into like a cylindrical pellet about 1.5 centimeters long, and then we stack those in hollow metal rods that are about 4 meters long. About 100 rods are bundled together to make a fuel assembly, and thousands of the fuel assemblies containing hundreds of tons of uranium are bundled into a reactor core. Okay, so in the reactor core, when struck by neutrons, radioactive uranium atoms undergo fission, and they release energy and more neutrons, and it triggers like a chain reaction, which, as I said, generates a whole lot of heat. Okay, the reaction is moderated in a power plant neutron absorbing cooling solution. In addition, control rods composed of neutron absorbing material are inserted into the spaces between the fuel rods, right? So water and other coolant is circulated between the fuel rods to remove some of this excess heat. If you didn't do this, the reaction would generate so much heat, I mean, it would melt the whole place. The greatest danger is a cooling system failure in a nuclear power plant, not an explosion, right? If that cooling system fails, then you get a meltdown that can release radiation. 70% of nuclear power plants are basically pressurized water reactors. Water is circulated through the core to absorb heat from the fuel rods and then pumped to a steam generator where it heats a secondary loop. So basically, this radioactive water never comes in contact with the water that, goes back out to the real world, okay? The secondary loop drives high steam turbine producing electricity. And like I said, you boil water, you make steam, it rotates a turbine, turbine's attached to a generator, and the rest is history. Under normal operating conditions, that pressurized water reactor releases very, very little radioactivity. Most famous accident in the U.S. happened way over on the East Coast at 3 Mile Island near Harrisburg, Pennsylvania. Reactor suffered a partial meltdown of the core, and the radiation release was minimal, but it set the tone. So this is what the ins and outs of a very simple nuclear reactor or pressurized water reactor would look like. Okay, so we're going to create that heat. We're going to boil that water. That steam's going to rotate a turbine. Turbine's attached to a generator, and bada bing, bada boom, we got electricity. Okay. There is a simpler but more dangerous design for a different kind of reactor, and this is a boiling water reactor. The water from the core boils again to make steam, directly driving turbine generators. Highly radioactive water and steam actually leave the containment structure, and chances of accidents are pretty dang high. There's also graphite moderator reactors. These operate with a solid moderator instead of a liquid. These are common in Britain, France, and the former Soviet Union. The graphite moderator reactors have been involved in probably some of the biggest nuclear power disasters in history. Chernobyl is probably one that you remember or are currently studying in history. Many of you probably don't even know about the wind scale one in England, right? There's also high temperature gas cooled reactors. In this case, uranium encased in tiny ceramic coated pellets, and helium is used as a coolant. If a reactor core is kept small, it can't generate enough heat to melt the ceramic coating, even if cooling is lost. There's not as many of these plants in operation. They are pretty safe. Okay. And then there's a breeder reactor. A breeder reactor creates fissionable plutonium and thorium isotopes from stable forms of uranium. They use plutonium that's reclaimed from spent fuel from conventional fission reactions as their starting material. The breeder reactor core must be like very, very high density. Thus, water can't be used as a coolant. Liquid sodium is actually used instead. The sodium is super corrosive and burns with intense heat, and it'll explode on contact with water. So there's that, right? A breeder reactor will self-destruct in a few seconds if coolant fails. Breeder reactors produce weapons-grade plutonium as waste. Okay? Now, the final issue really to think about when you think about a nuclear reactor is, like, what do we do with the waste, right? I mean, these fuel rods don't last forever. And when they're no longer of value for the production of electricity, like, what now? So the production of thousands of tons of uranium fuel usually generates 100,000 tons of tailings and 3.5 million liters of liquid waste. There's now approximately 200 million tons of radioactive waste in piles around mines and processing plants in the United States. And this is the kind of stuff, it doesn't break down overnight. It could take like thousands of years. About 100,000 tons of low-level waste, clothing, tools, and 15,000 tons of high-level spent fuel waste piled up around the United States. Spent fuel assemblies have been stored in deep water-filled pools in the power plants. Well, to just kind of get them out of sight, out of mind. But that's designed to be temporary. So, like, where do we put them, when we need that space? The U.S. Department of Energy actually announced plans to build a high-level waste repository near Yucca Mountain, Nevada, in 1987. So that basically means we're going to take all this nuclear material and, like, stick it in the ground. The radioactive waste would be buried deep underground. Funding for the project was cut off in 2009 after 20 years and over $100 billion was already spent. Russia has offered to store our nuclear waste, and other countries at Malek in the Ural Mountains. An explosion there in 1957 basically made the area the most radioactive place on Earth. So the Russians feel, well, it can't get much worse. So just bring all your stuff there and we'll just put it in the ground there. At the end of the day, like, what are we going to do? Okay. So, ladies and gents, this pretty much sums up our coverage of non-renewable resources. And I hope through these two videos, you've kind of gained a little bit better appreciation for, the good, the bad, and the in-between of each of these materials. I'm Mr. Kennedy, and I will see you next time.